Okay, welcome to Lecture 24 of Design of Mechanical Systems, Welding, Bonding, and Permanent Joints. So we've been talking about non-permanent joints, where we're using fasteners or bolts to achieve this joint. But the point is that we are able to disassemble this joint in case we have maintenance need or field assembly needs. Here we're going to consider the case where we actually intend for the joint to be permanent. And in those cases, we are using essentially two methods to do this. We are either going to weld the members together or use some kind of adhesive to perform a bond. So we're going to talk about this today, and we're going to start discussing first welding. So welding, as you probably know, uses a metal to join two pieces of metal, well, two or more. But the important thing is that you're using a metal to join two metals. But this joint is not simply depositing metal on top of other piece of metal. It is actually involving creating a metallurgical joint. And that means that there will actually be atomic bonding or alloying between the metal that you're using for welding, and your members that you're trying to join. And in fact, that is the most important ingredient on a successful weld, the fact that you are able to create a metallurgical joint. So there are different types of welding, and there are really many methods that we're not going to be able to cover. We're going to focus on some of the most common, and perhaps the most common one is arc welding. So in arc welding, as you can see on this figure, you're essentially applying a high voltage between the target piece and an electrode. And that electrode, which contains the material that you're going to deposit as a weld, happens to melt when the contact is established. Essentially, it's an intentional short circuit that is going to melt the electrode and a little bit of the target material so that you can create this metallurgical bond. You probably have seen the electrodes that are used for arc welding. You have a metal rod, which contains this is the metal that's going to create the bond. And there is a powder coating around it. And let's discuss a little bit what is the purpose of that metal that you have, of that powder coating that you have around there. So when the welding is happening, the arc is melting the electrode material so that you can deposit it. But in that moment, that is a high temperature process. And as with any high temperature process, that is going to be prone to create oxidation on the metals. And so this covering here, the powder coating that you have on those electrodes, is intended to create a gaseous shield. So it's going to create a local inert environment around the point that you're doing the welding, so that while the melting happens, the alloying happens, and finally solidification happens, there is an inert atmosphere around this process, locally where you're bonding the two or welding the two materials. So ideally, this is going to be a alloying process that happens very well, because you're not exposing the materials to the actual atmosphere that has oxygen and could lead to oxidation. So that's the purpose of that powder coating in the electrodes. Other methods of welding, for example, this is MECH, which is an acronym for Metal Inert Gas Welding. They use different methods, but essentially are trying to achieve the same thing. So in that case, you're still using an electrode that is going to be melting to for you to deposit the material that is going to form the weld. But then you also have a gas nozzle, and that gas nozzle is fed with some inert gas. Argon could be one example. And then it also creates this gas shield that is providing an inert environment while this metallurgical joint is happening here. There's a nice video in YouTube that you can that you can watch if you want to see a little bit more overview about welding. But this is about the depth of discussion that we're going to have as to the physical process of welding. As you know, in this course, we're trying to primarily focus on the stress considerations than when you do this type of things. So here we're going to focus on how do we analyze the stresses in this welding joints. So we're going to focus, like I said, we're going to focus on arc welding, but the concepts are going to be applicable to other types of welding, with some differences, primarily in terms of nomenclature, but the rationale and the process of analyzing the stresses is going to be similar. So for arc welding, if you've ever bought one of these electrodes, you will see that they have a specific code. So for example, you can go to the store and buy a 1613 electrode, for example, just to give an example. And this electrode number is defined by a standard and is related to the tensile strength of the material of the electrode. So the tensile strength that you're going to, or the tensile strength of the metal that you're going to deposit on the weld. You can see that these two numbers actually relate to the order of magnitude of the tensile strength. And so that's what the code tells you. Obviously, because these are different materials, there's also going to be different yield strength, and in general it increases as you increase the number of the weld. And then each of them is going to have a percent elongation, although there's really no monotonic relation between the electrode number and the percent elongation. But there is a relation between the electrode number and the tensile strength and the yield strength. And one important thing that you need to know is that all of this is specified in standards drawn up by the American Welding Society. So if you've ever trying to perform a weld or design a weld, you're going to need to look at these standards, because all that we're going to discuss is actually just a little bit of the fundamentals that are contained on those standards. And there are many more details. And if you really are going to design a weld for real engineering service, this is just going to be an introduction to that, and all the details will be contained on those standards. All right, so we talked about the stresses, and the other thing that we need if we're analyzing stresses in a weld is thinking about the geometry. And you've probably seen welds, and the common characteristic to all of them is that they have ill-defined geometries. It's not like you can say this has a specific geometrical shape, because it's really some sort of blob which has a varying geometry, and in fact the quality of this geometry is dependent on the machine or the person who does the weld. Welding is actually a very well remunerated profession, because some welders have actually very, very good skill and can make these fillets very, very uniform and very, very very homogeneous across a joint. And just from intuition, you can tell that that's actually a good thing, having a uniform weld. but in general, it's not going to have a defined geometrical shape. And so if we want to analyze the stress, and again, all of these are going to be estimations over which we're going to have to apply a factor of safety. But if you want to analyze it, we need to kind of idealize this geometry, this kind of ill-defined geometry, into something more amenable for mathematical analysis. So the first thing to note is that in general, there's going to be two members that you want to join. And then you're going to apply your weld, which has some strange shape, but most of the times it could be thought of as a triangle. And so we're going to draw a triangle that is fully inscribed into the geometry of the weld. And we're going to define a few dimensions in that triangle. And here are the dimensions. The two sides of the triangle are going to be called the leg. And then we have this part, which is the face. That's the hypotenuse of that triangle. And then the most important dimension that we're going to define is this perpendicular distance between the face of the weld and the corner of the triangle, and the corner is called the root of the weld. And this distance here is called the throat, T. And this is the most important dimension for the weld, and we're going to do most of the calculations of stress using this dimension. And so this throat, as I was saying, is the shortest distance between the root and the face of the ideal weld. The ideal weld, remember, is the triangle that we're using to inscribe the actual geometry of the weld. Okay, so the other assumption that we're going to make is that if you do a good job of welding, what's going to happen is that you're going to have an isosceles triangle, or in other words, the magnitude of the two legs are equal. And if that is true, then this angle over here is 45 degrees, and so the throat is going to be a square root of 2 over 2 of the dimension of the leg, and the square root of 2 over 2 is about 0.707. So if you do a good weld and you have an isosceles triangle, this is the magnitude of the throat in relation to the sides of this idealized triangle. Okay, now to know what are the allowable stresses that you can put in a weld, again, you're going to refer to the standard, or another word for this standard is the welding code. And the welding codes are actually going to have tables that tell you how much stress you can put in the weld. So for example, here we have a table for arc welding. So we have the different codes of the electrodes, which we looked at before. And then it tells you the allowable shear stress on throat, and this is in imperial units. And you can also do an alternative measurement of stress, which is actually not a force per unit area, but a force per unit of length. But they're equivalent, and we will do an example to see that these measurements here are equivalent to this one, or you can use both to do calculation of stresses. This one, if you know the area of the weld, you can just compare it with this. Or here, if you know the size of the leg, you're going to be able to compare force per linear unit, per unit of distance in the weld. But we're going to do an example to understand this. The other thing that is going to be specified in the codes is the minimum weld size. So this is the minimum side of that triangle, as a function of the pieces that you need to join. So for example, if you have a piece that is contained in a range between 1/4 inch of thickness and 1/2 inch of thickness, then the side of your triangle when you're doing the weld should be around 3/16. And so there's guidelines for other thicknesses, and you can just look at the table in case you need to design the weld. All right, we've been talking about stresses on the weld, but there's also going to be stresses developed in the members that you're joining with the weld. And the welding codes also are going to tell you what is the allowable stress on them. And that is actually dependent on the type of function that the weld is serving. So you can have a weld that is primarily used in tension or using compression, which is another way of saying a bearing load, or in bending or in shear. And here you have the type of weld. The terminology is similar to the shear welds that we looked at when we were looking at non-permanent joints with fasteners. But the important thing is that for each type of joint, the code is going to tell us the permissible stress as a function of the yield strength of the member material. Remember, here we're talking about the allowable stresses in the joint members, so this yield strength refers to the yield strengths of the material, of the member material. And just for your reference, these are the permissible stresses that are specified in the welding code for arc welding. And this is the equivalent safety factor if we put these inside the maximum distortion energy theory for failure. These are the safety factors that we would find if we consider these to be our von Mises stresses. And here there's a footnote that is going to be important in one of the examples that we're going to look. All right, so basically that's it for welding. There's some tables that you essentially just need to learn how to use. And so I think the best way to learn how to use it is just to do an example. So let's consider this example. And so we're going to have what it is called a tension joint, essentially because it's preventing a tensile motion. So here we have a base plate, and here we have another plate, and we've joined those with a weld here in gray. And we're going to apply a tensile force of 16.5 kips. Now, the cross-section of the bar has a width or a depth into the paper of 1/2 inch and is a rectangular cross-section. We have a 2-inch height, and the yield strength of the material of this member is 27.5 KSI. We're going to assume that the base plate is 2 inches thick, that the weld is performed along a length of magnitude 2 inches. And then the first thing I wanted to go over, you probably have seen this perhaps in the CAD course, but it's a good thing to remember. How do you specify this weld? How do you actually draw it in a technical drawing? So here we have a weld on 2 sides. And so we put an arrow, and then we're going to put this triangle here. And these 2 triangles actually mean that you're doing this weld here at the top and here at the bottom. So we have 2 fillets, and therefore we have 2 triangles. This is going to be the magnitude of the leg. So this is the side of those triangles, 3/8 of an inch, and we've taken this width from the recommended width that we see from the previous tables based on the thicknesses of these plates. And then you also need to specify what is the electrode that you're using, or the type of weld method that you're using. So this one we're going to do with an arc welding electrode that has this code. And remember that this code is actually going to be related to the strength of the weld material. So it's going to allow us to calculate, or to compare with the stresses that we calculate, to establish whether this joint is safe. All right. So I just give you here a view in cross-section of this weld. So this is as if we're looking from this direction. What we would see, we would have the 2-inch thick base plate, the 1/2-inch thick plate that we're applying a force upon, and then here is the weld fillet. And so what we're going to do is to start calculating stresses. So if we kind of blow up the weld and consider its geometry, what we're going to have is a triangle, right? Remember that we're idealizing that. So it's a prism with a cross-section as a triangle, and we're going to have shear stresses on it. And this is kind of important. In general, welds for the most part are going to be withstanding shear stresses. And so that's what we need to consider. And although we know there's going to be stress distributions that are probably complex, all these calculations that we're going to do are based on average stresses. Remember, we're trying to get an order of magnitude, and then we're going to apply a safety factor. So if we want to know this average stress, then we just need to do some quite simple calculations. So if I want to know the average stress, I would simply say the average stress, and it's a shear stress, is the force divided by the area, right? And the area in this particular case is the side of the weld multiplied by this length here, right? So I would say H over L. But remember that we said before that what is actually going to be important for a weld is the throat, this dimension here. And so again, this is one of those cases where we are using empirical observation to correct our calculations so that they are closer to reality. The reason we've been defining the throat is because it has been found by experience that stress calculations are going to be more accurate if instead of using the leg for a width dimension, you use the throat. So actually, we're going to do the average stress is the force divided by the throat and divided by the length. So force, we have it here, 16.5 kips. And then the throat, remember, if we assume this is an isosceles triangle where these two sides are of the same length, then the throat is going to be 0.707 multiplied by the side of that triangle, and that side of that triangle we get here from our specification of the weld, so 3/8 of an inch. And then the length. Now you can do two things. You can consider only one weld, but in that case you would have to put only half the force on each of them. Or we can consider all of it, and so I'm going to put all the length, the total length of the fillets in all the welds. So in this case I'm going to put 2 plus 2 inches. But it's the same, right? I'm applying the force and I'm dividing by 4 or I could take half the force and divide by 2. You just have to be consistent in these dimensions, and this just comes from doing a free body diagram of the weld. And so we have divided by 4. And so if I look at this dimension, or I look at this calculation, what I'm going to get is 15.6 kilo psi for stress in the weld. Now, this is the stress on this weld, and if the question is this joint safe, then I compare this with an allowable stress, which again comes from the standards. So if we look at the standards here, we go back to our table here, we look at the allowable stress for our electrode material. So we had a 7T series material, so this one, the allowable shear stress is 21 kilo psi. So if we go back to our calculation, this is less than 21 kilo psi, so yes, it is a safe weld. Now, I mentioned that we can do calculations based on stress. We can also make calculations based on force per unit length. So in that case, we would find the force per unit length, which is the force divided by the total length of welding. And so we would have 16.5 kips divided by 4 inches. We have 4.12 kips per inch. And then we go back to our welding code tables. And so here, but now instead of looking at allowable shear stress, we're going to look at allowable unit force per linear inch. So again, if we have a leg size of 3/8 and we have this electrode, we have that the allowable force per unit length is 5.57 kips per inch. And so if we go back to our calculation, yes, this is safe because 4.12 is less than 5.57 kips per inch. So what we've established is that looking at the weld, this joint is safe. But just like in a shear joint that we analyze for fasteners, we actually need to establish if all the constituents of the joint have stresses that are allowable. So we're not only going to analyze the weld, we cannot stop here. We actually need to go ahead and analyze stresses on this member, stresses on this member. And then when we establish that all of those are below the allowable limits, we can truly say that the joint is safe. Here we've just established that looking at the weld is safe, but we need to look at the other constituents of the weld. So let's look now at the base metal. So if I do a perspective view of this base metal and I remove all the other constituents, what I'm going to have is that there's going to be 2 strips here, and this is the location where the welds are deposited over. And just like this is undergoing that shear stress, then these areas should be undergoing a shear stress that is equal and opposite, right? And so, except now we're actually going to consider this area here. So let's do that calculation. So we're going to do a calculation now for the base plate. And so this is an average shear stress where we have a force divided by an area. So force 16.5 10 to the 3 kilo pounds divided by, and so we have this area here 2 times because we have 2 fillets, right? So 2 times the size of this dimension, so 3/8, and then the length 2 inches. So you see, it's very similar to the calculation for the weld in the sense that is an average shear stress. But when we were considering the weld, we're replacing the size of the leg by the size of the throat. But now, because we're considering the base plate, we are not doing that. We're considering the actual area. And so if we find the magnitude of this is going to be 11 kilo psi or ksi. And then again we need to figure out whether this 11 ksi is okay. Is this stress safe? So as always, we go to our code, and remember there was a table that specified the allowable limits in the weld members, not on the weld material, but in the weld members. So we have this table here, and what this table is saying is that when we have a tension joint, our permissible stress should be 0.6 SY, and then there's this other comment here that the shear stress on the base metal should not exceed 0.4 SY of the base metal. And so since we're considering the base of the joint, then this is the comparison that we should do. So what is 0.4 of the yield strength of the base metal? So we would compare with 0.4 of the yield strength of the metal, and I forgot to say this, but you know, these two plates have the same shear strength. So 0.4 multiplied by 27.5 ksi, that is 11 ksi. So what, and this is the allowable stress, and so the allowable stress is greater or equal than the stress on the base plate. Of course, look at the safety factor here. The safety factor is 1, so it is safe, but barely, because the stress that we have is the same as the allowable stress. Okay, so we found the stress on the base metal. We're missing one constituent in this joint, and that is the actual plate that is undergoing the tensile stress. So this one is joined by the fillet. So we're going to have an area here that has the fillet, right? But remember that we've already actually calculated the magnitude of that stress, which is using this area here. So what we're going to concern ourselves now is whether this plate is going to fracture like this under tension. And so that is a pretty simple calculation. We're just going to say sigma, which is a normal stress because this plate is in tension. Then we have force over area. And so we have 16.5 10 to the 3 kilopounds divided by the area, and that is just simply the cross-sectional area of this plate, which is 2 inches height and half an inch of depth, and so we have 16.5 KSI. And again, we need to figure out whether this is safe or not. And so we go back to our table that is telling us the allowable stress for the members of the weld. And we said here that for a tension joint, the permissible stress is 0.6 the use strength of the material. And so if we do that comparison, so the allowable stress is 0.6 multiplied by 27.5 KSI, so we get 16.5 KSI. So again, the allowable stress is greater or equal than the stress, so it is safe. But in this particular case, safety factor is 1 because they are actually equal, so it is barely safe. Not something that you would put in service, but I just wanted to illustrate through an example how do you make these calculations. Okay, so we've considered now what happens when we're applying a tension load to this joint. Let's do another example with this same geometry. So now let's assume instead of applying a tensile load, we're applying a vertical load here. So the first thing I would ask you is, what type of loading do we have in the weld here? Now, given that this is a virtual lecture, we're not going to have an actual poll, but I will ask you to think about this, pick a choice, and I'm going to make a pause here of about 10 seconds. So if you want to think about it, just pause the video, make a choice, and then after that you can unpause and I'll discuss the correct answer. Okay, so the correct answer for this is that this weld is subjected to both torsion and shear. Now, shear, if you remember, that's going to this is very similar to analyzing those shear joints with bolts. If you have this force here, it means that here at the centroid of this weld area, you're going to have a reaction shear force and a reaction moment. Obviously, there has to be a shear in the weld to compensate for this, and there must be also a shear to compensate for this moment. It's going to have a different direction, and that's why we say it is a torsion, but because it's sort of like if we're torsioning this geometry here. It's like if we're applying a torque in this direction to that geometry. So that's why we have torsion and shear. Now I have a second question for you. If that's the weld, if this is the geometry of the weld, where is it going to be the location of the highest stresses? So just as before, I'm going to stop for 10 seconds, pause the video if you want to think about it, and in 10 seconds I'll reveal the answer. Okay, so the location of the highest stresses is actually going to be on the corners, and the corners means here. And again, the way to think about this is very similar to this shear joints that were subjected to these torsional loads. So again, remember there's a shear here and a moment reaction, and the weld has to provide that. So just like before, as in the bolts, there's going to be a primary shear that is generated in response to this vertical load. So every single little infinitesimal element on this joint, or on this weld, sorry, is going to have a shear stress that is going to add up to account for this reaction. And we're going to call this, just like we did for bolts, the primary shear. But you also have a secondary shear, right? That one is in response to this moment. And so at every point on the weld, you're going to have little shears that are tangential to that rotation. And that's going what we call the secondary shear. And just like as we did with bolts, we're going to have to do a vector sum of those shears. And so in the corners, you're going to have a primary shear like this and a secondary shear like this, which is tangential. And so at the corners here, you're going to have the largest magnitude of the vector sum of these two shears. So the logic is exactly the same as those shear joints that we analyzed, where there is perhaps 1, 2, or 3 bolts put in there. So the magnitude of these primary shears, the primary shears is going to look familiar because it's just the shear reaction force divided by the area. But the secondary shear is actually going to be a torque because it's as if we were applying a torque to a cross-section that looks like this. And so just like any torque, we have a torque multiplied by a radius divided by a polar moment of inertia. Except here, we're going to have to do some special considerations due to the geometry of the weld. This is not like a cylinder in torsion or a tube in torsion. This is actually two fillets, so it's not kind of straightforward to think about what is the polar moment of inertia for that. So actually, we're going to use this formula. The polar moment of inertia is going to be some factor J sub u, which is dependent on the geometry of the weld, and the throat. Remember that when we are calculating stresses on the weld, we're going to replace all the weights by the throat, and this is an empirical observation that is known to work. And remember that the throat is 0.707, or square root of 2/2, multiplied by the length of the side of the triangle, which we called the leg, right? Remember, this is the throat. And so, for example, for this particular weld pattern, where we have 2 lines of welding, we have that this factor J sub u has this formula based on these dimensions of the weld. So here we have the length of the fillet, the separation between the fillets, and so you have here this Ju factor that you're Ju factor that you're going to use to find the polar moment of inertia. And you probably can anticipate that actually this J sub u factor has already been calculated for you and is tabulated for all kinds of different patterns of welding. So I'm going to show you that table in a minute. So here it is. It's actually present in the textbook in table 9.1. So you're going to look at what is the weld pattern that you're doing, and based on its dimensions, you're going to be able to find this J sub U, multiply by the throat to get your J, and then find the stress as you do for any torsional case where you have a torque, a radius, and a polar moment of inertia. Except that you're going to have to know in which location you have the maximum stress so that you know the radius. So just like before, let us actually go through the calculations of these examples so that we understand how to use these formulas. Okay, so let's first consider the weld. And then, just like before, we're going to find the shear stress. So remember that there is a shear force and a moment as a reaction to this force. And what we need to find is the shear stress related to that. So the first thing is the primary shear, which we signal with one apostrophe. And this is the shear that develops in response to the shear force. So we're going to have a ton of tiny shears here on all the infinitesimal elements, and that should add to the shear divided by the area of the weld. Now the shear force in this particular case is equal to the applied force here, and so we have force divided by 2 times, because we have 2 welds. Each of them has a length of 2 inches, and then for the width, remember, since we are considering the weld, we are not looking at this width here, but to the throat, which is 0.707, the size of the length, the size of the leg, sorry. So we get force divided by 2 multiplied by 2, 0.707, H is 3/8, and that leads to 0.94 F. Remember, this problem is a little bit different than the previous because we're actually trying to find the maximum load that can be applied safely, not the stress upon a given load. So we have 0.94 F for our primary shear. Now we need to find the secondary shear, which develops in response to this moment. So as opposed to before, we're going to have secondary shears that are tangential to this moment. So for over here, for example, is going to be like this, but then over here it's going to have this direction, and then over here this direction, and then what is the magnitude of that? So to find the magnitude, remember, it's a torsion, so like any torsion we have a torque, radius divided by a polar moment of inertia, but this polar moment of inertia is Ju multiplied by T, where this T is a thickness, or the sort of dimension that we use for all stress calculations when we talk about welds, which is the throat, right? 0.707 multiplied by the height. Now, the Ju I already have from this table here. So I essentially just have to use this equation, taking the appropriate geometry. So for Ju, I have this formula. And note that D is just length of the weld B is distance between the lines of the weld. So for this particular case, I have distance 2 inches, and distance between the welds happens to be 2 inches too. So I just replace this and then divide it by B. Sorry, divided by 6, as you can see in the formula, and so we get 5.33 inches cubed. And so simply J is going to be multiplying that by the throat. So 5.33 multiplied by 0.707, size of the leg 3/8 of an inch, and so we get 1.4 inches to the 4th power for J. And so we can find now the value of the secondary shear, which is moment, which in this particular case is force, this force. Remember, we're trying to find this reaction moment. The distance, the moment arm, is going to be to the centroid of the weld arrangement, which is over here, and since this happens to have 2 inches, there's 1 inch here and 1 inch here. So from here to here, there's actually 9 inches. Now the radius, since we've established that this vector sum of t prime and t double prime is going to be maximum over here, then our radius is going to be this distance here. So that's simply, since I have 1 inch here and 1 inch here, this is a square of root of 2 multiplied by 1 inch and then divided by J. And so if I do this calculation, I'm going to have 9.09 F. And so essentially what I'm going to have is that here at the corner of the weld, I'm going to have a vector going down of a magnitude 0.94 F and another vector here at 45 degrees, 9.09 F, and then I want to find the resultant. I'll skip the math here, you can find it in the notes, but it's just a vector sum, so it is nothing too complicated there. The resultant turns out to be 9.8 F. And so now we just need to make this shear equal to the allowable stress and then find the allowable force. So the allowable stress, again, we need to look at our welding codes. So we go back to our table that has the loading, the allowable loads. So here, remember, we're still dealing with a 70 series electrode, so the allowable stress is 21 kilo psi. So if that is our allowable stress, then 21 ksi should be equal to 9.8 F. And so we can solve for F, and F is going to be 2.1 kips. So that is the maximum force that we can apply such that the stresses on the weld remain safe. And just like before, we're going to have to repeat this calculation for all the components of the joint, not only the weld line, but also the two members, the two plates that we have here. So just like before, now let's go to the base metal. You can see actually that this calculation is going to be the same as the previous one, with the exception that the area and the thickness that we multiply this JU term is not going to be determined by the throat now, but we're actually going to use the size of the size of this triangle, because that's where the weld is making contact to the base plate. So the base plate has that stress, not the weld, but the base stress. And so what you can see is that the math is going to be the same, except this 0.707 factor is going to become 1. And so the vectorial sum is the same. I am not going to do it because it's the same algebra as the previous case, but you can see all the algebra in the notes that are posted in eLearning. In any case, the total shear, which again is going to be here at the corner, and again is going to be a sum of a primary and secondary shear, is going to be 6.9 F. And now we need to make this equal to the allowable stress for the base. And now, just like before, we go back to our welding codes that tell us the allowable stresses. And here we can see that the shear stress on the base metal should not exceed 0.4 the yield strength. And so we take that into consideration. So this should be 0.4, 27.5 KSI, which is the yield strength, and that should be equal to 6.9 F. So we have a force that is 1.6 kips. So this is the maximum force that we can apply, such that the stress in the base metal does not exceed the allowable stress. And then finally, after doing the base metal, we need to do the plate, this plate here. Now, this is no different from any other previous calculation you've done, because this plate is actually subjected to a bending stress. Remember, the weld is making contact here, and there's a shear stress associated with that, but we already calculated that. Now we're looking just at the other stress that is being applied to this plate, which is just bending stress from the force here. So that's not any different from any other calculation we've done. That's just MC over I. If you remember, the shear moment diagram of this is going to be like this, and so the moment is going to be like this, and so the maximum moment is here at the joint, and that moment is going to be force multiplied by the length, which is 8 inches here. C is the distance between the centroid of the cross-section and the top or bottom surface of the plate. So this distance here, we have 1 inch for that. And then the inertia for a rectangle, 1/12 the base multiplied by the height cubed, and so we get 24 F for that normal stress. We are going to make that equal to the allowable stress for a member, and remember, that allowable stress for the members is also in the code. However, before we were analyzing a tension joint. Now we are analyzing a bending joint, and here it's telling us that the permissible stress for the members should be 0.6 to 0.66 the yield stress. So let's apply that, and I'm going to use 0.6, given that that would give us a lower force, which is, we want to make sure we have the lowest bound for this force. So that should be equal to 0.6 yield strength. So in other words, 24F is equal to 0.6, 27.5 KSI, and so our force is 0.69 kips. So look what has happened. We found 3 different forces that lead to the maximum allowable stress in the three constituents of the joint. If we consider the bending stress, the force cannot be larger than 0.69. If we consider the shear stress in the base metal, the force cannot be larger than 1.6 kips. And if we consider the stress on the welds, that force cannot be larger than 2.1 kips. Obviously, we need to pick the lowest force, because if we were to apply this force in the other constituents of the weld, they would fail. So the maximum force we can apply is this 0.69 kips. But it gives you an example of why is it important to analyze the stresses in every single component of the joint to make sure they're all safe. And you take your bounds from that constituent that is more highly stressed, because if that's safe, then the others should be safe as well. So this is the maximum force that we can apply. Another lesson that you can draw from here is that actually the weld was more resistant than the individual members, the base metal and the plate. What we found is that to remain within safe limits for the stress, we could actually apply a higher force and the weld would not suffer, but the base metal and the plate would. And so that gives you sort of a lesson that applies for many types of welding joints, where the weld actually ends up being stronger than the members. So if you have a welding joint and it fails, what you will find a large percentage of the time is that the weld doesn't fail, or the joint doesn't fail because the welding material is failing. It fails because either one of the plates broke or some component in the joint failed aside from the weld. The weld itself is very, very strong. And I mean, it's a good thing because we want to have a permanent joint, but it just highlights the fact that you need to calculate the stresses in every single component of the joint, just like we did for shear joints in bolts and fasteners. All right, so that concludes the part for welding. This is how you would analyze the stresses on a welding joint. Now let's consider the next type of permanent joint. We talked about welding. Now we're going to talk about adhesive joints, where you're going to use a substance called an adhesive to create bonding between the members of the joint, and this is going to be a permanent joint. Now, the way to look at adhesives is by looking at their peel and shear behavior. Just like when you have a piece of tape, you can pull on it vertically, perpendicular to the surface to which it's bound. So that would be something like pulling your tape like this. And that is a peeling action. But if you have a tape and you pull it like this, that is a shearing action. So we have peel and we have shear. And the way we characterize adhesives is like this. We want to quantify what is their peel resistance and their shear resistance. Now, like I've been saying throughout the course, pretty much every situation where you want to quantify something about materials and related to stress behavior, if you want to do a test about that, most likely you're going to find an ASTM standard that covers that. And here is not the exception. There are standard test methods that you can use to characterize the shear and peel behavior of an adhesive that you're trying to test. So for the shear strength, you can have two plates glued with the adhesive that you want to test and just pull them apart and measure the force. And that's covered by this standard. Here we're looking at a lap joint. There's another type of test where you're testing the peel behavior. So here you have two flexible members that are joined by the adhesive here in the interface, and you pull them apart and measure the force to get the peel strength. There's another type of test which is very similar, except you're pulling 180 degrees like this. And so you're, instead of pulling vertically, you're pulling kind of in the opposite direction. And that gives you also a measurement of the peel strength. And so actually, when you buy an adhesive, and I encourage you to look at these, you can go to maybe Loctite, the website of Loctite, or the website of any other, perhaps epoxy manufacturer. You will find that when they sell you an epoxy, they will tell you the peel strength of this epoxy is this much, and it has been tested under this ASTM standard, perhaps one of these, and my shear strength is this much, and so that you can design based on these magnitudes. You want to make sure that the stresses that you have do not overcome the strengths that are quoted for that glue, adhesive, tape, whatever type of adhesive you have. But it is quoted by manufacturers. Now, here is a kind of an overview of more or less the orders of magnitudes that you get for these. This is from the book, and although it's a long table, don't think that this covers any significant percentage of the world of adhesives. The world of adhesives is incredibly vast, and you can find adhesives with a wide variety of properties. The ranges are very, very large. And so this just gives you a very, very quick idea of the orders of magnitude that you can expect. So here we have the type of adhesive, and we have the lab shear strength. That means this is the strength of the adhesive measured in this type of test. And so you have here a value either on megapascals or PSIs. As expected, epoxies have a very high shear strength, so they are good adhesive in general. And then you have things here like cyanoacrylates, which is super glue, pressure sensitive, which are essentially tapes, and other things like urethane. Those are chemicals that you use to achieve bonding. Now, what you see here is that you can also find peel strength. Except here we don't have units of stress, we actually have force per unit length. Now, how do we compare these two? I'll just tell you that adhesives will have more strength in shear than in peel. And I'm just going to try to use these numbers here to do an actual calculation with some assumed geometry to illustrate that point. So let's assume we have a joint, and we have a joint that has some width W and some length L. And let's assume that is 1 inch, which is similar what you get from standards. So if you want to find the shear force that it takes to break this joint, you would take the shear strength of the adhesive from this table here and multiply by the area where you are putting the adhesive on. And so you get a shear force. To get a peel force, you would multiply the peel strength per unit width and multiply by the length. So I'm going to multiply all these by 1 inch. And so what I did was I did this algebraic operation for all these different adhesives. So you can see what happens. What is the difference between the force you need to shear this adhesive or peel this adhesive? And so here are the results. And what you can see is that for every single adhesive, no matter what, the shear force that it takes to fail that adhesive is larger than the peel force. So this is a common characteristic for every adhesive. They are stronger in shear than in peel. And so If you don't remember anything else from this lecture on adhesives, remember that peel strength or peel force in adhesives is less than shear force. And that will give us some design recommendations that we will explore in the last slide of this lecture. The other thing I would mention about this is that essentially what you're going to do when you're designing an adhesive joint is just like the other types of joints, you're going to try to find the stress on the adhesive layer. So if there's an area here, and I'm drawing this on 3D, maybe let me draw it here. This has a length L and a depth, let's call it D, into the paper. So the shear strength, the shear stress there would be the applied force divided by that area. But remember, this is always an average stress. And for the particular case of adhesives, that actually is not so much a good approximation of what actually happens. So just to give you an example, if we have these loads and lengths, the average stress in this particular joint here would be 2000 divided by 2, just because we have 2 adhesive surfaces, and then 1 inch by 1 inch, so we have 1000 psi. If you actually make that calculation using a full elasticity theory and compare this average to what actually happens, you will see that the average, although is within the same order of magnitude, actually underestimates the maximum stress that happens. And it can be almost double. And it can be even more depending on the geometry. However, this calculation is not straightforward. It changes depending on each different geometry. So the message here is that if you're designing an adhesive joint, yes, you're going to calculate this to give you an idea whether you're on the right ballpark. But to actually make sure it's safe, you're going to have to calculate the exact stress distribution. And that's beyond the scope of the course, but I will tell you that that follows a mechanics theory called the shear lag theory, in case you're interested, and maybe will be covered in intermediate mechanics of materials or more advanced mechanics course. So you have to do that to find this maximum, and then you can design based on this maximum, or you have to use a large safety factor. I would say larger than 3 if you're just going to calculate this, just to make sure that this real variation of the stress is not too far from what you design based on the average. And now the last point that I will make connected to this, which is also connected to what I was saying, that peel strength is much smaller than shear strength, is that when you design joints, you must design them such that they're using the adhesive in shear rather than in tension. So here there are some examples of a bad design if you're using an adhesive, and a good or improved design. So let's go case by case and understand what is happening here. So if you put adhesive here on this case, what you see is that here there's a moment, right? And so right here at this point, you're actually, if you take a piece of the adhesive, you're actually trying to stress it like this. In other words, you're trying to peel it. And so here you'll have peel, and that's not a good use of adhesive. As opposed to that, in this case, if you do moments over here, you're still going to have peel, but the moment arm is smaller than this one. So even though this design is still using the adhesive in peel. I mean, there's also shear force because if this is the adhesive, there's also shear like this, right? But there is peel over here in this corner. But remember, it is less here because the moment arm of the force is smaller here than in here. Because here the moment arm is this one. So that's how you improve this joint. Here, if you try to kind of pull this in this direction, obviously here you're pulling on the adhesive, so essentially you're trying to peel it, which is not good. Here, if you originally bonded this, maybe it was like this, and then now you pull on it and then it achieves this shape, you can see there's a lateral motion of that plate, which means you're using the adhesive initially in peel, then at the very end is in peel. But because you're using initially on shear, that constitutes an improvement of this of this joint. This one here is quite obvious actually. Here you're really pulling on this adhesive in this direction. So you're using the adhesive in peel. Whereas here, you're using it actually in compression, because you're using the contact here with this plate to cancel that peeling action that you were doing over the adhesive. Here, if you do sum of moments here, you're doing a peeling action over here. That is canceled if you use this like this, because although there is moment over here, the reaction is pressing on the adhesive layer instead of peeling on the adhesive layer. And here there are other examples which follow the same logic, where you're trying to modify the constituents of the joint or the geometry of the whole joint such that you're using the adhesive in shear rather than in tension or peel. So this is the very kind of the most important message related to adhesive joints. Like I said, if you don't remember anything about adhesive joints in a year, remember this: you must use the adhesive in shear instead of using it in peel. Okay, so this concludes our lecture on permanent joints. Thank you for your attention.